Alrighty, welcome back to our last video for this week. If you are watching them in order for the environmental science class. So we just talked about how environmental policy has been helpful in helping, figure out environmental issues that are occurring through through our actions and just what we're doing in our day-to-day lives, or what companies are doing, to have a good and better economy. So your book, and also I want to go into ozone depletion, and something that wasn't necessarily a policy, but more of like a global coming together, if you will, of being like, oh, hey, something is wrong. We need to change that. Otherwise, it's not going to be good for us. So let's get into it. Starting off actually with talking about just the overall structure of the atmosphere. So this is kind of my bread and butter. I am an atmospheric scientist by trade. So this is something that is very, concerning to me. So what we're looking at here, this graph on the right-hand side, is temperature of the atmosphere, as the relative temperature of the atmosphere as we go up, with temperature on the x-axis and altitude on the y-axis. And we can see that the atmosphere is split into different layers. So we have the troposphere. So pretty much all of the weather that you've ever known and loved and experienced in your whole life has occurred down here in the troposphere. It extends about 10 kilometers roughly high. And then you have the stratosphere. And this is the layer that we are going to focus on when we're talking about ozone. And then we have the mesosphere, the thermosphere, and then we do have a bit of an atmosphere beyond these particular layers, like the exosphere and the magnetosphere. But those do their own amazing little thing that we're not going to focus on necessarily in this class. So what we can see, what happens with temperature on average, is that it decreases as you go up. And that makes sense, yeah? So when you look at a mountain range, and the Sierra Nevada mountains right now are absolutely gorgeous with a lot of snowpack. So they are higher up in elevation. They're able to sustain that snow during the winter months, right? And then you get to a point, and the level of where we go from troposphere to stratosphere, that varies around the world, right? So in our in the equatorial regions, where it tends to be much warmer, the air is less dense, so it's physically thicker. So the stratosphere is a bit higher there, whereas in the polar regions it's much colder, so the air is physically thinner. So it's actually why we see jet streams where we do. Really, really quite fascinating stuff. But what we are concerned about is, of course, in the stratosphere, this component being ozone. So our atmosphere is mostly comprised of oxygen and nitrogen. And then this ozone layer here is in the stratosphere. And that's why we see this sort of slight warming, or something called a temperature inversion, in that layer. So looking at the overall composition of our current atmosphere, nitrogen reigns supreme at about 78%, oxygen coming in at a very far second at 21%, and we always kind of forget about argon, but she's still hanging out at about 1%, and very, very small concentrations of neon and helium. And then these are the variable gases of some moist air. So we got water vapor, carbon dioxide, methane, nitrous oxide, and ozone. We're of course going to focus today on ozone, but these other varying components are also important as well, but they haven't been specifically targeted by policy at the moment, or by a global outrage, if you will. So perhaps you've heard of this lovely little thing, ozone depletion, or the ozone hole. So the ozone hole exists over Antarctica every year because of something called chlorofluorocarbons, or CFCs. And that breaks down ozone when the sun interacts with the atmosphere. And this is most pronounced in the southern hemisphere spring, summer months, but there are other little holes as well, but this is the one that's most concerning. and we'll talk about the chemistry breakdown here in just a second. So thinking about it this way as well, you have to have the interaction of the sun linked into this idea, because it's once there's that chemical reaction of interacting with heat, that's when the breakdown happens. So you need that, and that happens in the southern hemisphere, right, in like September, October-ish. So we need ozone. We need ozone in the stratosphere. This is actually one of the reasons that scientists believe that animals moved from the oceans in onto land. Like that shift probably happened thanks to ozone and making it not so hot and crispy down here on Earth. So it helps absorb that harmful radiation so we don't cook to death or get really bad cancer or, what's called sunburns. But this is a global issue, right? So this affects everybody. And it has been in process of healing since about 1987, thanks to an international agreement called the Montreal Protocol. So this was back when we believed scientists, when they sang the alarm bells or rang the alarm bells. So some folks who started monitoring just over Antarctica, they were noticing this hole as it appears, every year. And these are measured and called Dobson units. So just like your body temperature is measured in Fahrenheit, it's just a unit of measurement for this particular feature. So in the troposphere, back here at the surface, we don't like ozone down here, but we like ozone up in the stratosphere. Ozone down here at the surface is really, really bad for human health. When you have a smoggy day, whether it be up here in the Bay Area or down in Los Angeles, you can literally physically see like the smog layer. It's actually pretty gross. But we like ozone in the upper atmosphere. So don't like it down here. We like it up there, right? And I do also want to mention that this isn't a permanent hole necessarily, in that it's not persistent throughout the entire year. So once the reaction kind of gets used up, then the hole will heal. So this here is looking at September 24th, 2021, and then the following February 2022. So you don't see those dark purple or blue hues, but we can, so it's something that kind of fixes itself in a sense throughout the year. But what we're concerned about, what scientists are concerned about, is the overall size of this hole, right? We don't want it to be as big as that. We would like for it to be much, much, much smaller, right? So that's what we are observing at the moment. That is thankfully healing. However, it's not something that happens quickly, right? So with Mother Nature, she takes hundreds of thousands of years to create something, but she can take seconds to destroy something. So it's just something that's going to take time to really fully be realized or be seen. She doesn't work on our time clocks. She works on her own. Looking just a little bit further at the reaction that happens here of ozone in the stratosphere. So ozone is naturally created and destroyed in the stratosphere over time. And that's from the oxygen molecules interacting with UVC. So there's basically three main ultraviolet wavelengths that we consider. You have shorter wavelengths or hotter, more energy, in like this darker red. And then you have UVB and UVA. And so what happens is UVC interacts, or UVB interacts with ozone, so O3, and then it naturally forms and breaks as the molecules absorb those rays, right? And then UVC can break them, UVB can make them. And so that's where we get kind of concerned, right? I really like this visual, by the way, of how it shows the UVA and B being the ones, the rays that penetrate down to the surface, whereas everything else is absorbed here, which I think is really cool. then there's this unnatural breakdown from CFCs that are not found in the atmosphere naturally. So CFCs consist of chlorine and fluoride and carbon. So it's easier to call them chlorofluorocarbons. So it's really the chlorine part that is the catalyst to this reaction. It really helps speed it up. So if CFCs were not released into the atmosphere, then we wouldn't have that unnaturally there. And CFCs were produced for good things. They were like, it was from aerosols, but also helping refrigerants and air conditioning units, like cool down, I think. So it's like their initial purpose was good, but it's the environmental impact down the line that we didn't even think about seeing, right? It wasn't something we were like, we didn't use NEPA to test this theory to see if it would actually work or not work, right? So, sometimes policies like that happen, right? But thankfully, as we got through, and scientists were like, hey, this is not okay. Let's come together. So we're like, all right, cool. So here's our protocol. So this is a graph that we could expect, or that we would kind of like showing different scenarios. If there were no protocol, what would happen to the abundance of stratospheric chlorine or CFCs? What's happened, thankfully, thanks to the Montreal Protocol, the London Amendment, Beijing Amendment, or zero emissions. So other amendments also call out for the phase out of ODS replacements that are greenhouse gases to help address global climate change. So I do also really want to mention here that it's kind of a common misconception, or just a maybe sort of, I don't know if misinformation necessarily, but sometimes ozone gets into the conversation when we're talking about climate change and greenhouse gases. That's not necessarily the case. And the ozone hole is not causing climate change. So I just want to squash that one now before we move on. So it is harmful, right? It is definitely an environmental impact. I guarantee you and can confirm that getting a sunburn in Australia, when their signs everywhere say, hey, put on extra sunscreen because there's the ozone hole, and I'm like, I tan. And no, I turned into a little lobster. It was not great, not fun. So it is a problem. So it really goes to show with the Montreal Protocol that we can come together as a world, and we can decrease the emissions of these harmful molecules, and perhaps try and do better for our future planet. Again, that's just one of the many environmental policies that are out there, but I think it nicely shows that we can actually do something about a problem that we see, and it sometimes isn't always a very fast reaction. Even though we're a society of needing things quickly, we just have to work with Mother Nature's timescales. All right. So thank you so much for watching, and I hope you have a great rest of your day.